Greetings, my name is Professor Duke Orata. We are continuing with our lectures, and today we want to look at jet propulsion. Jet propulsion engines. Now, we want to discuss propulsive work from the aircraft power plant. That is our main interest today. And one of the first things which we need to indicate clearly is that suppose you have an aircraft which is flying horizontally at a constant velocity. Let's call that velocity C1. Just make a note here that I want to focus on propulsive work from aircraft power plant. So let's say that we have this aircraft. Let's just draw some image of an aircraft. Let's say that's an aircraft and it's flying at a constant velocity. Flying horizontally at a constant velocity. I call that C1. Now, when this aircraft is moving forward, it experiences aerodynamic forces which resists its movement in the air. So we can think of that as kind of air resistance. So the aircraft, as an aircraft flying horizontally at a constant velocity, very important, C1. As an aircraft flying horizontally at a constant velocity and experiencing aerodynamic forces opposing its forward motion in air. Think of that as air resistance. Then for this particular aircraft, which we have just drawn some cartoonish form of the aircraft there, so it's not, but you get the point. It's flying at a constant velocity horizontally. Of course, it experiences aerodynamic forces opposing its movement. Aerodynamic forces. Let's just call them ADF. The dynamic forces opposing its movement. Now, the drag in this aircraft, so we normally refer to that person, you can call it drag on the aircraft. That drag, the aircraft, for that drag on the aircraft, there will be an opposite and equal thrust. There will be an opposite and equal thrust, which is a force against this drag here. There will be an equal in the first place and opposite thrust or force. Let's call it Fn. So since this aircraft is moving at a constant velocity C1 and the thrust is Fn, then the rate of work done is simply the product of this thrust times the velocity. The rate of work done and I underline the word rate. As I've always mentioned in all the lectures where we have mentioned rate, anytime you see the word rate, time is there. So the rate of work done will be a C1 times Fn. And why is it called rate? What is C1? That's velocity. Remember, from dimension analysis, what is C1? That's velocity. That is distance over time. And what is Fn? That's the force. So what is this quantity? Force times displacement is work over time. That gives you the rate of work, because that's work over unit time. Very important to always remember. Anytime you see the word rate, always remember time is there. Now, we have two important classes of propulsion engines. We have two classes of propulsion engines. One is one where atmospheric air is the propulsive fluid. It's the propulsive. The second one has its own fluid, like for example in a rocket motor. Its own propulsive fluid. The example is a rocket motor. In general, for these propulsion engines, we can have a schematic. It has one or more of the components which we are going to show there. Normally it has a nozzle, it has a source of energy, and it has a diffuser, a source of energy, and a propelling nozzle. So for the schematic for a propulsive engine, propulsion engine is such that we have, there's a schematic. We have source of energy. We have a diffuser. And we have a nozzle. That's V2, velocity 2. And of course, we have atmospheric pressure. Atmospheric pressure. What is P? What is P? So we have a diffuser, we have a source of energy, and we have a nozzle. And just to remind ourselves, we have had several lectures on steady flow and jet propulsion. And one of the things which you had mentioned, which you need always to remember, we said that in the case of a nozzle, we have accelerated flow. Always remember that. And the pressure is normally reduced. And if we remember, we talked of a pressure wave, where we said that A squared was minus V squared del P del V and a constant entropy. This was a shock wave or pressure wave. Recall that. And we also said that for the duct, we have the expression VdP at 1 over c squared minus 1 over a squared. That we attributed to, we put it as sound wave. And we mentioned that in the case of the nozzle, when C as the velocity, remember we had that duct, that was a stationary duct. Always remember that. Now, when we are talking about the aircraft, this is something possessing motion. So unless the velocity is constant, then you can consider it a stationary duct, then there will be, the calculations will not be so far away from what is expected. But if, because it's possessing motion and you take that into account, then the calculations have to be altered. So this was a stationary duct, remember? And we say that when CA is less than A, then what are we talking about? dA was negative. In other words, what does that mean? dA is negative. In this particular case, when CA is less than A, then dA was negative. And what does that mean? That is convergence. And when CA was greater than A, dA was positive, and that is divergence. Very important to remember these things. And in the case of the diffuser, where we have decelerated flow, decelerated flow, that is dP increases, pressure increases. When CA is less than A, dA is positive. That, of course, is divergence. And when CA is greater than A, dA is negative. That is convergence. And remember, when CA is greater than A, this is supersonic flow. Always remember that. And so it's very important to remember these quantities. So as we are talking about the diffuser and the nozzle, you need always to remember this. But remember, this was in a stationary duct. So what are we talking about? We are talking about absolute velocities. That's the velocity relative to the Earth. And so when we are talking of the duct which is possessing motion, then we'll have to give our velocity a new term. And we have, as we progress, we'll see how we do that. Now, it's important to note that the diffuser and the nozzle are not part of this piston engine. The diffuser and the nozzle, the propelling nozzle, are not part of the piston engine. Always remember that. And so, in the case of, for example, a turbojet engine, we have the diffuser, we have the nozzle, and the source of energy has three components. We have the compressor, we have the combustion chamber, and we have the turbine. In this case, the source of energy includes us as a compressor, as a combustion chamber, and a turbine. Always remember that. That source of energy, in the case of a turbojet engine, we have a compressor, combustion chamber, and the turbine. Very, very important. But what you need to remember is that because the aircraft is moving and there's build-up in pressure, there's increase in pressure. When there's increase in pressure, then we don't need a compressor and we don't need a turbine. And that brings you to what we normally call a ram jet engine. During aircraft fast movement, the pressure rises significantly. The pressure rises significantly, therefore there's no need for a compressor and of course a turbine, because that's the one which drives the compressor. There's no need. There's no need for a compressor or a turbine. And this new situation is the basis of the ram jet engine. That's the basis of the ram jet engine. This particular situation there is the basis of the ram jet engine. Ramjet engine. So it's very important to know that. So in the ramjet engine, we only have, so in the ramjet engine, in the case of the ramjet engine, we have the diffuser, you have the combustion chamber, and you have the nozzle. And so always remember that even in the turbo jet engine, when we talked of in the source of energy, we have the compressor and we have the combustion chamber and we have the turbine. The turbine does no work. Remember that. Note that. In the turbo jet engine, the turbine does no work, no significant work. And if at all it contributes, then the high energy air which comes from the turbine gets its way into the nozzle, the propelling nozzle, and we have a high-speed jet. That's about what it does. So in a nutshell, so what are we saying? So probably, insignificantly, the high energy air from the turbine gets into the propelling nozzle, producing high speed jet. That's about it. And so, as I mentioned, when we did our earlier discussions, we had a stationary duct. And so we were talking about absolute velocities, which are velocities relative to the Earth. But now the duct is moving. And so, like, for example, when you're talking of the ramjet engine, for the pressure to build up, it means you have to initiate a motion. And of course, we have the piston engine, which will do that because that piston engine drives the propeller. Also, the other thing to note, so let's call that one. The second note is that in the ram engine, for pressure to build up, we must initiate motion. Or velocity. And this, of course, the engine, the piston engine, the mechanical work